Great. Okay, so this presentation is entitled Characterization of Initial Fire Weather Conditions for Large Spring Wildfires in Alberta, Canada. Thanks to Canada Wildfire for holding these knowledge translation and mobilization sessions. I'm a big fan of KTM, so I'm keen to present some of the results, which is one of the chapters in my thesis. So the whole, the big motivation for this research was a 7 days in May event in 1968, May 18th to the 25th. And I was particularly interested in knowing whether the 1968 7 days in May, the synoptic weather pattern, surface and upper, and then the associated strong and persistent south-southeast winds were the predominant spring weather pattern during extreme wildfire behavior in Alberta. And this kind of ties somewhat to Dante's presentation that he just gave, because these strong, persistent winds blow 24 hours. So they have a very strong effect on the burning conditions in the night, and particularly sustained and very, very strong desiccating winds. So I was really interested in quantifying, is this really the issue? Is this really the big one, the big synoptic weather pattern that we need to be concerned about? So I selected wildfires that started in May and exceeded 1,000 hectares in size for the period 1990 to 2019, resulted in 80 wildfires. You can see them on the map there. The big fires I labeled, those are the fires that are greater than 100,000 hectares in size. Of particular note, they're all in the predominantly the boreal plains ecozone. In the boreal, fires were excluded from the national parks. Sorry about that, national parks folks. Be interesting to actually put some of that data in, but that was excluded. And what I did is I focused on the first 4 days of wildfire activity. Essentially since the time that they were reported. I looked at the global ERA5 reanalysis data set. We used the information from these grids to calculate FWI code and indices. How did we identify a spread event? Well, day one, if the wildfire exceeded 200 hectares, or the noon ISI was greater than or equal to 9, then you were a spread event. On days 2 to 4, if the wildfire size doubled in size from the previous day, or the ISI was greater than or equal to 9, those days were considered as spread events. And if gusts were reported from the nearest Alberta's weather station, I took the 10-minute average wind speed and adjusted it to a maximum 1-minute average wind speed. And this is kind of based on Crosby and Chandler's data set that they published. And so we used a piecewise linear function. But what I did then is with the wind speed adjustment, I then subsequently readjusted or recalculated the FFMC and the ISI values. The big effect on ISI, less so on FFMC. And so the whole point here is that if I just included gusts to calculate my my FFMC and ISI, I'm going to overestimate. If I don't include gusts, I'm going to underestimate. So this was an approach to kind of include gusts to determine whether there was a spread event. So for the period 1990 to 2019, I had 8,838 wildfires. So yeah, 80 of those were larger than 1,000 hectares in size. Why 1,000 hectares? Well, I had to find a compromise in terms of the size of the data set, but also these fires, when they get to this size, I mean, they're basically campaign fires. You're going to get a level 1 incident management team in there. These are big fires, and they're the ones that are causing the damage and the concern. 50 of them were lightning, 30 were human caused. These resulted in, I temporally and spatialed these fires into what I refer to as spread event groups. And this just facilitated an analysis of the weather patterns. But overall in these groups, or these number of wildfires, there are 123 spread event days. For the lightning fires, they occurred on 79 calendar days. The 30 human caused wildfires, I had 89 spread event days. They'd occurred on 70 calendar days. And when combined, I ended up with 92 combined individual calendar spread day events to focus on. I looked at FFMC ISI BUI median values. I calculated the bootstrapped 95% confidence intervals. So in this case here, and then I calculated these indices for all the wildfires for the entire period. And then I broke it down by cause, lightning and human caused. Looked at 2 periods, period 1, 1990 to 2004, period 2, 2005, 2019. And then looked at period both by cause. So interestingly, so you'll see for all the spread event days, the median, I used the median, was 91, and the 95% confidence interval 90 to 91. And then likewise ISI, BUI, and then the paired cells that are colored, they indicate that there's a significant difference between the periods. I looked not only at the spread days during those 4 initial days for all 80 wildfires, but I also looked at the non-spread days. And then I repeated this analysis, looking at the median FFMC ISI and the BUI. And so you'll see that the FFMC dropped from 91 to 87. The big one was the ISI. It dropped from 13.7 on the spread days to 4.4 on the non-spread days. And as expected, the BUI didn't change that much. Went from 47.5 to 45 for all fires. And interestingly, the only paired cells looking at the periods was the BUI. The significant differences between period 1, period 2 for all fires, and in particular lightning fires. And those are big increases. So suggesting a climate change impact there. So the spread event groups that I looked at, they were characterized based on looking at the surface weather maps from various sources, but predominantly NCEP. Likewise, the surface and then the 500 hectopascal maps. We had a couple of websites that we looked at. And we identified prefrontal and frontal passage activity for those spread event groups. So here you can see the different combinations of patterns. So the top one, for example, surface trough or low, upper ridge or upper high. And then we identified them by a specific pattern, the total spread day events, whether there was prefrontal gusts, frontal passage gusts, or just gusts. And so 41% of the spread day events, the pattern was a surface trough low with an upper ridge high. Not surprisingly, 70% lightning caused, frontal passage related. And then 36% of the spread event days were tied to this 1968 sort of the event that I was targeting. And most of these were human-caused fires. So the spring wildfire regime in Alberta, wind-driven, very high to extreme FFMC ISI. Very high to extreme BUI values are not a prerequisite for extreme wildfire behavior. The predominant feature associated with the 92 combined calendar spread day events was a prefrontal or frontal passage, 48%, almost half of the 92 calendar spread day events. And then the strong southeast winds, similar to 1968, 7 days in May, they occurred on 26% of the 92 calendar spread day events. And then I also looked at days when there was just no large wildfires that started. And because these winds can have an impact, even though there are no wildfires, but they occurred on 10% of all days in May for the 12 years when there was no large wildfires that started. That was in the data set that I used. So we built maps, surface and upper maps, and just showing some examples here. This is the Slave Lake wildfire on the left, and the characteristic feature of the Hudson Bay High, and then a surface low kind of to the southwest of Alberta. And what we're really looking for here is a strong pressure gradient. So on the top maps are the surface, and the lower maps are the upper with the. And then likewise for the frontal passage, I'm going through these quickly. I'm just cognizant of time, but this is the Fort McMurray fire. I believe that's May 4th. Yeah, and the cold front passage that's swept through the town of Slave Lake and the supporting upper ridge below. So I've only got about 1 or 2 minutes left. So opportunities for enhanced preparedness and research opportunities, further research. Large spring wildfires in Alberta are wind-driven, as we noted, and just a small percentage of wildfires, it only takes a few days, but just a small percentage of the spread days in the spring are associated with these critical synoptic weather patterns. And the key one for me is the wildfires in May are predominantly human-caused, 83%, and they've caused all of the structural losses virtually in Alberta. And you can see here that incendiary fires are a problem in Alberta in May, 11.9% for May. Looking at the entire year, 6.3%, it's almost doubled. Lightning, 17.2%. So this is a human-caused fire, for sure. Opportunities. Well, one of the things that I found is that for sure the prediction of critical weather patterns are important, but what I found more interestingly is not just the identification of these critical weather patterns, but how they evolve. The supervisor of the weather section told me that they knew 10 days in advance when the fire went into Slave Lake that critical weather pattern was setting up. And that really blew me away. And so I don't have the time here to show, but I went back 10 days to take a look at the evolution of these critical weather patterns. So I think this is an area of further research, is really better understanding the evolution and the tracking of how these weather patterns set up. So on May 4th, there was a surface high pressure over the Arctic, and you could really see how this pattern evolved. And there was an early warning for that when the wildfire entered into Slave Lake. Wind extremes and variability associated with gusts. We do a really poor job of incorporating gust in for fire behavior analyst work. Climate change impacts, our data analysis showed that there is definitely a strong difference in the time periods. Atmospheric stability and low-level jets were not taken into account, so there is a real opportunity there to maybe take this 80 case fires, the large fires, and look at this. The key for me is the use of precision prevention regulatory tools. I think this is where Alberta really needs to shine and put a little bit more effort. 55% of the area burned comes from May wildfire starts, but you don't see 55% of our wildfire management effort focusing on May. So this use of precision prevention regulatory tools where you're very strategic in time and place and putting them on quickly, removing them quickly when you need them. And for sure in Alberta, there's real opportunities for stronger integration between the fire weather forecasters and the fire behavior analysts. I won't get into the details in terms of how I think Alberta should do that. I think that's up to Alberta. And one of the things I found, there's a real opportunity for increased understanding of the linkages between the surface and the upper synoptic weather patterns. I think more needs to be done in terms of weather training for fire behavior analysts in this area. And particularly, one of the things I found from my perspective learning and just the position of existing wildfires in relation to these upper ridges. Are they on the down? Are they on the upslope? Are they on the west side or the east side? How does that impact what's going to be happening down that road, in the next couple of days, as that upper ridge moves? So lots of opportunity, I think, for further research. Some of that's already going, and we're going to hear more of that for the rest of the day. I just wanted to show here that in 2004, Alberta changed its fire reporting system. The arrows show where there was wildfire reviews that were done. The red arrows indicate that there is a very strong El Nino. So whenever there is a very strong El Nino in Alberta, we are in trouble in May. I mean, that's very, very clear. So there's an opportunity for looking at teleconnections, and in particular teleconnections and climate change. How are they related? And for further details, I just refer you to a paper that was, as Brian mentioned, just published in the International Journal of Wildland Fire. I'd like to thank the Department of Renewable Resources, University of Alberta, Alberta Wildfire, Canada Wildfire, my supervisory committee. This was work that I did as part of my thesis. And the co-authors of the paper, Dr. Mike Flanagan and Dr. Puce Jane. And I was a little bit rushed. I'm over. My apologies, but thank you.